Hello, welcome back and to our first session on cover meters. So just for a bit of bookkeeping before we begin, I will start each presentation on time and I will endeavour not to run over. So we'll go through the full content and I'll break before the next presentation and let you know when that will be. So for those of you who are just joining, this is PCTE's New User Day. I'm William Ward and I'm the New South Wales Manager with PCTE. We're here live with an audience in Silverwater. On the board we've got Joel, who's running our communications for me. Say hi, Joel.
Hey, everyone.
And so if you've got any questions or requests, please do let us know on the live chat, or you can unmute when I ask for questions and we'll play them to the room and see what we can do. In terms, we are recording this, so please do be mindful of that, and we should be good to go on the first presentation. So it's going to be about cover meter theory and operation today. I spent a lot of time talking about cover meters because while it's a really commonly used tool in industry, it's maybe one that you're going to see some misunderstandings about. So I try and address those misunderstandings, tell you what a cover meter is good at and what a cover meter is bad at in this presentation. I also will show you an operation procedure so you know how to use it, and we'll talk about other ways to check cover, like when we get to ground penetrating radar a little bit later today. Just 1 second and I'll get going. Joel, you need to Okay, so let's begin on this first presentation. So when we look at the kinds of energy we can send into a concrete element, we choose the energy we want to use based upon the sensitivities we want to have inside that structure. So electromagnetic energy, like magnetism, electromagnetic induction or pulsed eddy current induction, or our ground penetrating radar tools, all of those are going to be more appropriate to find metallic embedded objects. And when we go to radar, we've got some sensitivity to non-metallic and some geometry measurements. But if we're looking for voids or defects, typically something air or cracking or damage to a structure, we'd be more likely to go ahead and use the ultrasonic tools, which is what we're going to cover on the last session of today's presentation. First question, why do we measure cover? Why is cover such an important thing to address as an engineer or a structural inspector or someone doing QA? It's because the durability of the structure is very heavily controlled by the cover depths of the reinforcing. What you'll find is that if we're talking about chloride-induced corrosion or damage to the structure, corrosion caused by carbonation, you'll see that all of those, the first and best protection is solid, uncracked, undamaged concrete with sufficient depth above the reinforcing steel to give the expected design life. So when a durability designer does his best to plan out what that structure's life will be, that's where input of things like the cover will be involved. So with the cover meter, in addition to checking before the concrete is cast, we'll be able to check after. Joel, if you could just bring up number 3 on that, that should let the audience have a quick read of the slide contents. Thank you. So if you see, look at this example on the left of this. We have the carbonation induced curve. We can see that in that case, we can take a 10-year reduction with a couple of millimeters of cover deficit. So this is partially why we use cover meters over ground penetrating radar or other tools. They're actually precise enough to measure a couple of millimeters difference. You won't get that same precision with a ground penetrating radar. And we see again, similar calculation, 5 millimeters cover down, 10 years off the life of that structure. So before I start telling you how they work and what we use them for, I want to give you a mental model that if you learn nothing else today, I want you to understand this about your cover meters and how they are built and brought to you by the manufacturers and how you should apply them on site. The suppliers calibrate them, so when you get your calibration certificate and you see it's been checked typically to 60mm bars, 15, 30, 60 and 90 in the case of the Profimeter PM8000. And the estimate function is checked on that calibration block as well. They are doing their calibration to a single isolated metal bar with nothing else around. So it is purely, can it take the measurement it intends under a simulation of an infinite bar in an infinite block. That's great. That gives us a lot of confidence in the machine is working, and every Profimeter or other cover meter is the same as every other cover meter produced by that manufacturer. But it doesn't give you the certainty you need on site to know it's going to work for your job. So the other aspect you need to watch out for is how do we as users of these tools have a verification on site that lets us understand the machine's measuring our job correctly, because that might be 200mm bars, 60mm bars at an even spacing, a very simple job. Or it could be something really complicated in infrastructure where you almost need a test method plan and a repeated process to measure in a reliable, repeatable way on that element. So first thing, your machine works. The manufacturer and us as the supplier have checked it. But for the sake of your job and the work that you're going to do, it's better that you also have your own records, that you have a process that's going to achieve the desired goals on site. And the second thing is the real mental model to be aware of with cover meters and to understand when it's going to work well and when you're going to have troubles. It's a box that is sensitive to metal. Yes, that metal can be rebar. And if it is rebar, well and good. It'll be operating as intended. But anything metallic will be detected by an eddy current cover meter like the Profimeter. So if we have cables, if we have lapped reinforcing, which is going to be extra metal, and if the machine is just a box that's sensitive to metal and we're measuring the depth of that metal, that means that it can underestimate the cover because of the additional signal. We also want to watch out for interference. Don't wear watches, sort of keep steel cap boots if they're metal away from the cover meter, and work to find that ideal circumstances, which is that single bar isolated under the cover meter. And that's the process I'll teach later. The other thing is, because it is only sensitive to metal, it's sensitive to metal rebar. We're not going to get any signal response from carbon fibre or fiberglass reinforcing. Now out at PCTE, we represent ProSec, so we have their PM8000 cover meter range, the PM8000 Lite, the PM8000, the PM8000 Pro. I'll do a little demonstration of the different operating modes they have and highlight where they set apart later today. But practically, there's everything in this range from a device that simply finds the bar and gives you the depth of that bar to ones that can do the kind of area scan, color mapping presentation projected onto images like you see here. It's all the same measurement technique, just a different functionality available from the machine. Now, what's the machine actually doing? I said it's a box that's sensitive to metal. What do I mean by it's a box that's sensitive to metal? Well, it's an eddy current device, so we're producing an alternating current electromagnetic field, and we're placing that in the vicinity of a reinforcing bar. We're measuring the amount of signal response that comes back from that bar, and we're converting that to depth. So it's not a ruler, it's not a physical measurement, we're not measuring directly the depth of the bar, we're measuring a signal intensity that we convert to the depth of the bar. And with the cover meter, there'll be a couple of inputs we have. We'll give it the size of the bar, so an assumed or measured bar diameter. And we may have a couple of corrections we can use if bars are close together, or we need to make some other adjustments to make sure the measurements bang on. So if you're doing very critical forensic surveys, big, large-scale durability work, yes, you've got a non-destructive tool, but like with all non-destructive tools, you'll also want to have some destructive evidence, expose some bars, measure their sizes, check the depths, and use that to put in a really good input to get a really good output from your cover meter. Just to highlight a little bit more about the eddy current, to give you an illustration of that working, we have a transmitting coil, or in the Profimeter several transmitting coils. They will receive a pulsed eddy current actuation, so they'll turn on and produce an electromagnetic field. So the current flowing through the steel will produce its own electromagnetic field, and once that's been produced, we're then going to turn off the transmitting coil and measure the signal intensity on the receiving coil. And it's the intensity of that return signal that we convert to depth. What affects that signal? Well, the first thing that affects that signal is if we move the bar higher or lower. If we move the bar higher, the signal will increase, and if we move the bar lower, the signal will decrease. And that increase or decrease, so as it goes, that increase, that decrease is going to be big, because the signal responds a lot with a change in distance. This is why when we use our cover meters, we say that we can take a very precise measurement. I'll talk about exact precision, but up to a millimeter accuracy with a well set up calibrated cover meter on site. But there's another thing we can do to that coil. We can change the size of the bar in the coil. And if we're changing the size of the bar, the issue is going to be that that's a very small change. So I'm going to say this now, and I'm going to keep saying this throughout the presentation. Your cover meter is a reliable tool for measuring the depth of bar and has some ability to locate those bars, though I don't encourage the use of cover meters for clearing targets before drilling or cutting. That's not appropriate. But the diameter estimate function, because of the very small change on the test and some of the interference issues I'll discuss later, it's an estimate and it may fail. So it will either give a reasonable value that's not very precise and shouldn't be used for things like strength analysis, or the device is going to not perform. It'll tell you it can't do it, or it'll tell you it can't do it indirectly by giving you a ridiculous number. So do watch out for that diameter estimate function. It's appropriate in some cases, but it's a very limited functionality. Now, limitations for general cover meters. You've got a maximum range of about 150 to 180 millimeters, and that depends on the bar size. The smaller the bar, the more shallow it needs to be for us to locate it correctly. The deeper the bar, the less shallow. I've already pointed out lapped reinforcing bars or closely spaced reinforcing bars. All of those add more metal, so increase the signal, so they will appear artificially shallow. Doesn't mean we can't use the cover meter for a quality check, but it does mean that we don't want to do it with default settings. We want to have a process and a sort of mock up or test it on the reinforcing before it's cast, or to an exposed bar, so we know we're getting the right measurements in the right contexts. Also, if you've got very congested, very unusual reinforcing layouts, or it's a structure you just know nothing about, maybe GPR has some role to play there, even though it's not as precise. Now, we don't want to use the location functions when bars are quite close together and deep, because if we do that, we'll find that yes, the cover depth can be set up to give an accurate number, but the unit's no longer going to lock onto and indicate the position of its targets. Some of the visualization functions will also be less useful in that context, though the line scan visualization is great because it tells you when it can isolate bars and it can't isolate bars. I always like working with a line scan visualization. I do apologize for the motorcycle outside. Okay, range and accuracy. First rule when you're setting up and using your cover meter is you're going to want to keep it in the shortest range that you can while using it. So if you've got a standard or a short range and a deep range, you'll keep it in the lowest standard range. If you've got something like a spot range as well, something that's trying to get into corners, you wouldn't use that unless you have to use it. So because the standard ranges tend to have the most rejection of interference, they're the least troubled. Whereas if we turn to a deep range, we're sending out more energy, we're working in a mode that is more easily interfered with. So yes, it'll let you go to a deeper depth, but it's more easily interfered with. So your precision, just scaling out, we're going to start from a 1mm precision out to around 50 millimeters, and that's also where your standard range of measurement will typically end. Then we're going to be going up to a 3mm precision, out to the 100mm range, and then out to the end of the performance, we're sort of 4mm, 5mm precision at the worst range. And if you look at your cover meter, you'll see that's what we check when we do our calibration work. Now, what's the big question people ask when I tell them they've got to enter the bar diameter?
How do we know the bar diameter?
How do we know the bar diameter? That's exactly right. And the answer is, well, ideally you've got records so you check. And if you can, you're going to get the best performance. But sometimes it can't be done. Sometimes we need to rely upon other ways of working. And one of the things we can do is we can actually look at the variability and that uncertainty. So if we're going to, as an engineering judgment, we go, look, this bar could not possibly be bigger than 30 millimeters, or could not possibly be bigger, like in this example, than 20 millimeters, and it could not be smaller than 8 millimeters. We can actually look at the additional uncertainty. So we can see that in this case, we'd probably underestimate depth by maybe 3 millimeters, 4 millimeters, but we could overestimate it by up to 15 or 16 millimeters just because we're not certain of the bar size and we've left it at the default 60 millimeter setting. So it's good. It's helpful to understand that, but it shows why what you need to let your clients understand about the precision of your measurements. Keep this in mind with any non-destructive tool that is being used to take numerical values. They're not rulers. Even rulers, you need a manual to use to understand how to take a precise, repeatable measurement. Once we go to a non-destructive tool where there's inputs and interference, it's your job to let your client know. Or as a client, if you're here as a client, to understand that what you're asking your site team to do, there's limits to the performance of the tools. And if they're saying, I think we can do this easily, or this is going to be more difficult, it's worthwhile to bear that in mind as you plan out your quality control work. So I'm going to go a little bit onto the diameter estimation functions now. So firstly, how do they work? So the diameter estimate functions, they will move between the standard and the deep range. So the reason that's important is, what did we say? Deep range is more easily interfered with. They also are not configured based upon the bar diameter you entered. So you can't put a guessed bar diameter in and improve the diameter estimate. It's always just a raw performance based on signal at standard and signal at deep. That means if we have reinforcing within 150 millimeters, extra steel, apparently larger bars. An important hint on the eddy current style tools, because they can essentially form a current loop if the reinforcing is electrically continuous, they can be very poor performers if you're using them in welded reinforcing or even tied reinforcing. A fairly straightforward application where we just maybe do some location work, or do we have to have an entire record on a precast element that's heavily reinforced telling us to check 50 millimeters in from one side, 30 millimeters in from other side, with a configuration that's proven to measure. And from that, we'll choose the kind of cover meter configuration we might use. We'll choose the documentation we'll use, maybe if we're going to set up the data logging functions in a device. If you do intend to use data logging on any non-destructive tool, I hardly recommend it, but it's good to practice and learn them before you go out and use them in anger. And if you've got a report to do, what's going to go into that report? What evidence and visualization do you need for it? So a couple of gold case studies. We'll start in the left corner of the room and go around. If we've got a minimum cover value of 40 millimeters, it's a slab on ground. Do we need anything particularly special in terms of the cover meter? Or can we use something simple?
I mean, it depends on what you're trying to find.
Sure.
But
I don't see why you couldn't just, see,
Absolutely. It's
kind of where the average kind of values and then where the bars are.
It's not a particularly elaborate or difficult job, but what if we go to something a bit more difficult, same 40mm cover requirements, but maybe some additional reinforcing, some very tight bar spacing, 10 centimetres apart. How does that change things? What do we need to be aware of now?
Would you have some interference from the other bars around you?
Yep, exactly. So if you're using the profimeter, you might use some of the neighbouring bar correction functions or other resources like that to assist you to measure that precisely. What about if we've got an unknown residential floor and it's a suspended slab? Is that likely to be conventionally reinforced?
Yes, it is.
Residential flooring?
Not conventionally, but then we'll have to look at where the laps are, where the spacing, if it's double reinforced or single reinforced.
Yep, exactly right. Once you get towards structures that have higher performance requirements, you need to either know something about that structure or you need to do some further investigation. Something I will highlight is, particularly in high-rise residential, you might also have post-tension construction or other details, and a cover meter is a cover measurement tool. It's not a tool for locating and measuring post-tensioning. What about if we want to do some scan before drilling work? What are we going to be able to do with a cover meter, and what are our limits with a cover meter's performance on scanning before drilling?
I think you mentioned before we shouldn't use the cover meter.
That was the hint waiting.
Yeah.
So the thing with cover meters is when we're doing a scan before we drill, we're not typically doing it to find a bar. We're typically doing it to avoid hazards. So the hazard might be cutting reinforcing or particularly cutting post-tension tendons and reducing the capacity or integrity of the structure. Working on some infrastructure projects, they're very sharp about not touching any of the reinforcing. But also it's a safety for the drillers. If you've got power or plumbing or other hazards in that structure that could harm the person doing that work, they're not going to be detected with a cover meter. Yes, it might be interfered with a bit of electrical cabling, but it won't see it won't let you know it's there. The other thing is there's quite a severe depth limitation on cover meter surveys. They go 150 millimetres, barely the thickness of a pretty naff slab on the ground. You're going to want to use radar for the additional depth penetration, the additional sensitivities, and the ability to locate multiple layers of targets and multiple types of targets, including non-metallic. Now, the other goals to keep in mind, if you're doing some structures for dilapidation or before remediation, what are some of the concerns we might have there that we wouldn't have with doing quality control work with a cover meter? What's going to come up differently?
I'm not sure.
It's okay. This is all just to have a discussion. It's just to, if nothing else, keep everyone awake.
Dilapidation survey, inspection for remediation.
So talking to the mic, please.
If you're doing remedial work, your cover meter is not going to be able to find you any defects. It's just finding
absolutely
metallic objects only.
Yep. The reason that I do highlight cover meters for dilapidation or remediation is that durability aspect. When we go and we do our half cell potential and our corrosion discussion this afternoon, we're going to actually talk about a lot of things that tell us, is the steel rusting, or how quickly is it rusting, or what's the concrete like. But an underappreciated part of a durability assessment is how deep are the bars and where is the salt or the contaminants, how far have they diffused in. So you would use a cover meter as one input on a durability survey, along with chemical analysis for carbonation and chloride depths, and then maybe some of your electrochemical corrosion methods. They form a set. Just doing cover or load isn't going to quite give you the whole picture. Okay, thank you. So, how should we use a cover meter? This is a process to take an accurate depth of bar. Because if we just take the cover meter, see that it's got a number on the front, drop it on the surface of the concrete and go job done, that number won't be accurate. You're simply unlikely to place it in a position which is correctly oriented. You want your cover meter to be placed directly on top of a reinforcing bar and to be away from any additional metal so that you are measuring accurately. So to do that, we actually need to learn how the reinforcing is in place on site. If we're using our cover meter, and it's a reasonably straightforward locate, we can find the bars in one direction. I'm not going to take any numbers the cover meter gives me because I'm just locating the bars. And I'll do this again, moving my cover meter with its measurement point. So on a profimeter, that's the crosshair which lights up and indicates the position of the bars. There's also some lines on either side showing the midpoint of that. We move that measurement point through the middle of the reinforcing bars. By doing that, we've reduced as much as possible the interference. And if these bars are spaced more than 150 millimeters apart, that's all we need to do. We've got a good number there, and we can go in and out and check the bars in the other direction and see if they're a bit closer to the surface. At that point, I've got good numbers. Now, if I discover the bars are closely spaced or I'm maybe not getting good locating work, first thing I'm probably going to do is go half a meter above or below my spot, because if I'm on lapped reinforcing, that normally gets me away from lapped reinforcing out in the mid-span of a mesh. Quite helpful. If ever you wonder why isn't it working, go up, go down, try and find a better spot. And if you find that you can't isolate single bars, you might need to do some investigation to discover how the spacing and layout is and put that into your cover meter so at least your numbers are accurate. So again, ideal positioning, a single bar with nothing else around it, or bars spaced at 150 centres or further, because then you won't have any other influence. Once the bars get closer than 150, there is a functionality called neighbouring rebar correction. You can tell it how close the longitudinal and latitudinal bars are, and if they're different sizes, you can tell it the size of each bar diameter. With that, you're going to pull an accurate number out, even in a source of interference. With lapped reinforcing, or measuring where there's other metal underneath your device, you're not going to be able to use an automatic setup. In this case, your only choice is going to be to take a drill, work out your bar position, and adjust your cover meter settings till you get an accurate locate on a bar that has sufficient cover. Because at least then you can use that for quality control. But the measurement depth will never be precise. It becomes only a sort of pass-fail tool. We lose that measurement aspect once we have lapped bars, or we can't get away from closely spaced reinforcing. So do watch out for changes in bar diameter and additional bars turning up where you don't expect them. And do watch out for bar orientation. People are human. You can't assume that your bars line perfectly perpendicular with your walls or floors. So always do the proper scan to locate the real path of the targets before you take your measurements. Once we get to more complex layouts, you need to have some idea how it's built, whether that's a GPR scan before you take your cover meter depth measurements, or it's drawings, or it's having a look at the reinforcing cage before the cast occurs. You're going to want to have your picked spots where the cover meter will measure accurately with or without neighbouring rebar correction. That's the secret to more complex jobs. And again, I know the question is sometimes, well, we just don't have that information. Well, then it needs to be fed back to your client. If we can't do some destructive investigation, or you don't have some records to give us, or we can't get the GPR scanner out and increase the scope of the job, your depth precision on a quick cover meter check isn't going to be there. Just manage expectations. Now, let's look at a cover meter in action. Firstly, just pure bar location on the PM8000 cover meter. So it will detect the presence of bar, and when we line up on top, we see the center of that bar, and then we can use that to find the centered position. And in this case, because I can see it, I don't need to know the location of the horizontal bars. But if I was doing this really properly, I'd have found both of that and done a few chalk marks before I took my numbers off. Because this is a PM8000 or PM8000 Pro model, I do have a memory functionality too. So I'll be able to turn on the data logging, line it up on the bars, tell it to record that value, or tell it to record that value and give me a diameter estimate. And that spot measurement is going to give you a data log record. Do we have some comment in the corner?
No, I'm just saying it's much cooler than the cover meter we use.
Oh, good. And again, this is just the basic functionality. If you're using a Profoscope cover meter, the previous model from the manufacturer, you would be able to do the same kind of collection and import, just with a Windows application. So in this case, I make a file, a folder, and I can pull in the data log record I just took. It doesn't know how, because I didn't use the wheeled scan car, it doesn't know how close the bars are. It just gives a measurement of each bar position. Once we do put on the scan car, we're now going to have some visualization. We're going to be able to represent the signal strength across the line of travel. And this is good for two reasons. One, because a picture is useful to convey more geometric information. The bars are this closely spaced and they're at this depth. But even more importantly, when we're using a tool which shows us the signal strength, we can identify if we've got some interference. So you can see there, those three closely spaced bars, the signal doesn't fully die down as I cross it, so maybe I could have used a little bit of neighbouring rebar correction in that measurement. Now if I use the same tool on the wall, I'm going to have rather than mark up on the Profometer, we've actually got a top and bottom detection, so I can balance the signal, so I know I'm as far away as possible from bars above me and bars below me before moving. And then I'm just going to cross over, locating the bars, getting the clean spacing between them. And this is just the mode which shows cover depth, but if I swipe down with 2 fingers on the iPad once I finish my scan, I can see my signal intensity, and we can see here the signal goes up and down. So we've got really clear detection of individual bars. There's no signs of lap or uneven spacing. When I go to one of the grid measurement modes on my PM8000, I've got a functionality called a multi-line scan. I've also got a 3D scan. The multi-line scan is very useful because it finds the closest bar in each cell as I pass my cover meter over the cells. The reason that that's good is I can use that to pair with other forms of non-destructive testing data. Back to that half cell potential. If I know the depth of the closest bar to the surface in a region of my structure, and I do half cells in the same region, and I keep my grids identical between the two, I now know whether they're likely corroding and how close they are to the surface. And maybe if I've got some chemical analysis, I can start to form relationships and do some thinking on the corrosion and durability side that is enabled by this visualization. You never want to take a pretty picture just because it looks good. You want to be able to use it to answer a question or explain something to a client who isn't familiar with the tool. If you're doing visualization, you're doing data logging, you'll be doing it because you want to do statistical analysis, you want to present your data in particular ways, or working in assets like that. So just to show this in action again, multi-line scan, so we see it's a single line lined up over the reinforcing. And I give it my exact spacing. Now the spacing is good because if I've got 200mm bar spacings, that's probably my grid. Unless maybe I just define my grid by my corrosion grid, then I'd do my corrosion grid, but I'd still try to, as much as possible, keep in between bars when I take each line. We want to always account for interference. We always want to know that bar layout and account for interference using the tool. This is even more important when we use the full area scan functions, which I'll show you as the last video, because when we use the full area scan functionality, what our limits are then going to be are going to be based on, we just can't have other metal. If we want a clean X and Y direction reinforcing bar layout in area scan mode, we have to isolate individual bars or they start to get messy. It's why it's much better, I think, to use the multi-line scan for most jobs, because that functionality is intended to visualize closest bar critical cover information. XY direction bar is more of a structural concern, and you'd probably use a radar for it in most cases. But I particularly like this. So this functionality is more appropriate, I think, for cover surveys. So again, building up that, I might just skip forward a little. So we can see that we get that bar position, and we get the cells of compliant and non-compliant cover based upon where I put my slider, like that. Finally, this is marking up for an area scan. So in this case, I'm going to locate each bar, and I'm going to take its position. So I know all my horizontal bar positions, and I'll write that on my wall before I start taking the 3D visualization. And once I've got that positioning, I'm going to be able to get the different depths and plan out my survey. So we know this was 200mm bar spacing, so I'm putting in 200mm bars, and that's what I'll put into my grid on my device. And once I know that layout, I can do it the same in the other direction, get my vertical bar spacings. It's the same, find the position of a bar, know the space between them, and get that marker position onto my tape, giving me everything I need to do a proper grid visualization. This is the process I showed as an animation being demonstrated live, and you have to do it if you want to use the grid spacing, because now you put the spacing between bars in as your grid, and then you have enough information to take an accurate value. If all you had done was just go, you would find that when now I take the scan, I would have bars all over the place. The additional interference from not being cleanly oriented would prevent my visualization working effectively. But now I can center in between each bar, I know and we get a nice clean vertical bar detect. We'll do 3 lines picking up the vertical bars. And then we'll do the same picking up the horizontal bars. And again, because of that attention to detail, I get a clean visualization. So that's now if you do use the area scan functionality, because it is a Screening Eagle or ProSec radar, we also have the augmented reality presentation. So with a marker at the origin, I can project the position and heat map of those bars onto my structure. And that's sort of a full demo of the PM8000's current general operation. I do have a more detailed webinar about PM8000 operation in particular I've done previously, but there's just to give you a good overview of what's achievable. Joel, if we could bring up the number 1, thanks. So that's the finish of the cover meter training information, sort of to give you enough to understand them, specify them, use them in action, and to show a little bit of the PM8000. Do we have any questions from the room or from the chat? You're welcome to unmute. We can just turn up the sound a little, and we should be able to hear you in the room if you've got any questions. And Joel, if you can also read out any questions that come in on the text chat. Just change over to your cell phone too when you do. So questions from the room? Nope, we don't have any questions in the room. Any questions on the live chat? All right, so thank you very much. That's the first presentation for our new Users Day. The next session is going to be our GPR scanning session, starting in a little over 45 minutes at 10:30. So we'll be putting the stream to sleep but leaving it live, so you're welcome to hang out, listen to the very chill music while we wait, but I'll see you at 10:30 for our GPR session. Joel will be presenting and Hugh, our National GPR Manager. Thank you very much for joining us for the first session.